In this video, we are going to discuss the estimation of a new population parameter, which we call as the population proportion of success. So to explain, we assume that a binomial experiment is being conducted. So for the population, you have a population size of capital N, and by a binomial experiment, we mean that there are only two possible outcomes, the success or the failure. So capital X here would refer to the number of successes in the population. So the proportion capital X over capital N is the population proportion of success denoted by the small letter P. For the sample, we do the same thing. So you have a sample size of small n, and out of the small n samples, you only have small x number of successes. So this proportion which we obtain from the sample is denoted by P hat. Okay. And as we will later see, P hat will just be the best estimate of the population proportion P. Okay, so the best point estimate for the proportion of success P is P hat. And the 1 minus alpha 100% confidence interval for P is given by this formula. So again, take note, P is the population parameter, which should be unknown. So that is the value we are trying to estimate. And you have here a confidence interval for P, which would have, again, a similar structure as our previous formulas, wherein you have the point estimate P hat, and then you just add and subtract a margin of error. So for the estimation of the proportion of success, we are again using the Z distribution. So we have here Z of alpha over 2 multiplied by the square root of P hat Q hat over small n, where P hat is the sample proportion of success. Q hat is just the proportion of failure from the sample. So that is just the complement of P hat. And small letter n is just your sample size. So let's try to illustrate with an example. So in a random sample of 500 families owning television sets in Quezon City, it was found that 340 subscribed to Destiny. So find a 95% confidence interval for the actual proportion of families in the city who subscribe to Destiny. So first of all, we are already given a sample size of 500 and 340 successes. So our P hat would just be 340 over 500, which is 0.68. So as a best single value estimate, we can already say that 68% of families in the city subscribe to Destiny. But we want to set up a confidence interval. So let's now try to fill in all of the missing values in our formula. So we have P hat equal to 0.68. Q hat will just be the complement of P hat. So that will just be 0.32. Also, we have the sample size to be equal to 500. And we want a 95% confidence interval, which means alpha is equal to 0.05. So we are looking for Z of 0.05 over 2, which is Z of 0.025. And again, you can check with your Z tables that this value is equal to 1.96. So plugging in to our formula, you have the following. Okay. And on the upper limit, it's just the same, except that you're adding the margin of error. So you will have 0.68 minus 1.96 times the square root of 0.68 times 0.32 over 500 and 0.68 plus 1.96 times the square root of 0.68 times 0.32 all over 500. Okay. And you can try to verify that the answer to this is 0.6391 and 0.7209. So we are 95% confident that the interval 0.63 up to 0.72 will be able to capture the true proportion of families in the city who subscribe to Destiny. Okay, so we went from a point estimate of 0.68. We extended that to an interval of 0.6391 to 0.7209. And this is with 95% confidence. Now, similar to our estimation of one mean, we can also set the sample size here so that we can minimize the margin of error. Okay. So if we use the sample proportion as an estimate of P, we can be 1 minus alpha 100% confident that the error will not exceed the value E when the sample size is given by this formula. N equal to Z alpha over 2 squared P hat Q hat over E squared. So going to our previous example, how large a sample is needed if we do not wish our error to exceed 0.02 at 95% confidence? So Z of alpha over 2 as mentioned earlier, this is just equal to 1.96. Okay, so the sample size will be given by 1.96 squared times P hat, which is 0.68, times Q hat, which is 0.32, and then just divide that by E squared. So you do not want the error to exceed 0.02. So that is the value that you plug into the denominator, and make sure you also square 0.02. Okay. So if you try to compute this using your calculators, okay, the value that you will get is 2089.8304. And again, you just round this up to get 2090. So you would need a sample size of at least 2090 in order for the margin of error not to exceed 0.02.